Hi, I'm Ping Chen, a PhD candidate under Distinguished Professor Bing-Ching Wei from National University of Singapore. The title of my paper is Blockchains versus Distributed Database, Dichotomy and Fusion. Since the moment that smart contracts have transformed blockchains from a cryptocurrency platform into a generic data processing system, its similarity with the conventional databases has been under hot discussion. However, the existing works focus on their distinct properties to external applications. For example, they propose a flowchart to guide practitioners for their decisions. In the meantime, many practitioners also notice database and blockchain share abundant similar technical concepts, from contracts to store procedures, consensus to replication, from cross-chain swap to inter-share transactions. However, we observe all these discussions are rather scattered. Our work aims to provide a unified taxonomy that encapsulates both systems under a generic distributed transaction platform. But why is that necessary? It serves two purposes. On the one hand, a unified taxonomy helps to explain the performance in a fine-grained manner. For example, Blockbench empirically demonstrates blockchains for performance is far from behind from databases in both YCSB and small batch workloads. This conclusion is rather intuitive and meets plenty of details. For example, what factors account for this magnitude level difference, and why the gap for the small batch shrinks? On the other hand, there are emerging a variety of database blockchain hybrids. By matching their designs into our taxonomy, we can provide a reasonable behavior prediction for future system designers. Our taxonomy consists of 4 independent dimensions. They serve orthogonal purposes and induce corresponding challenges. Replication copies data into replicas and brings challenges to synchronize them. Concurrency aims for more parallelism, but must regulate their interference. Storage trade-off between the access efficiency and data verifiability. Sharding partitions data for scalability and make tricky for cross-shard transactions. In later slides, I will label the performance-favored design in blue and security-favored designs in red, so that it is clear to say that databases occupy a position on performance end of spectrum, permissionless blockchain on the other end, and permission blockchains in between. The replication can be further broken down into 3 sub-dimensions. The replication model deals with the basis to replicate it on. Both types of blockchains replicated on transactions due to the presence of the ledgers. Database storage replicated as replication work upon operation logs. In replication approach, we differentiate a consensus-based approach with a primary backup approach by whether there exists a view change mechanism to fail over the leader replica. Apart from the above, we classify a share log approach, in which systems outsource the replication task to an external log producer, such as Kafka. We observe all 3 replication approaches in distributed databases, but all except the primary backup in permission blockchains. Permissionless blockchains all adopt the consensus-based replication. In terms of failure model, permissionless blockchain assume for the Byzantine behavior and databases only with a crash failure. Note both failure models are observed in permission blockchains. We put asterisks on permissionless blockchains, and they have to additionally mitigate the cyber attacks. In concurrency, permissionless blockchain takes an extreme precautionary approach to execute transactions serially based on their ledger sequence. On the one hand, it makes the behavior more intuitive. On the other hand, due to the slow consensus, concurrency will not help too much on speed up. Databases, in a favorable performance, exploit much concurrency as possible as long as not violating their isolation levels. Permission blockchain ride the fence again, like Fabric. Due to its unique execute order validated architecture, it executes or simulates transactions parallel, but commits their effects in a sequential manner. In terms of the storage, all contract-based permissionless blockchain provide a verifiable organization to provide their states. They mostly achieve it via Merkle tree variants. On the contrary, nowadays database direction is to optimize the storage to better harness the hardware. We notice that some permission blockchain directly utilize the off-the-shelf hardware optimized storage like LevelDB, while some others additionally build a Merkle tree on top. Despite this, all blockchains explicitly maintain a ledger abstraction for the full history, where conventional databases only keep limited history logs for recovery. Blockchains assign data to shards in a node-aware manner. Security can be reflected that much efforts are to avoid Byzantine adversary corrupting any shard. In contrast, we observe databases dynamically adjust a workload assignment to smooth the bottleneck. Another perspective is how they implement the 2PC for cross-transaction atomicity, where databases employ 2PC with a single transaction coordinator. Permissioned blockchain at another level of guarantee by implementing the 2PC on-state machine replication. There's no central entity or group in permissionless blockchains. A cross-chain transaction is separated into decentralized sub-transactions, each to be carried out by participants by their incentives. Based on our taxonomy, we broadly classify all blockchain database hybrids into two categories. Out of the blockchain databases provide the database abstraction to users. Internally, this database is powered by a blockchain for the security. Out of the database, blockchains attempt to implement a decentralized ledger from a well-established databases. Hence, the former are all storage replicated, where the latter replications is on transactions. But as we have seen this red box, in other dimensions, both types of hybrid system have a mixed preference with respect to their own security performance trade-off. In the experiment, we evaluate the following systems: TiDB to represent NewSQL database, etcd for NoSQL one, Quorum for permission blockchain with conventional order execute paradigm, and Hyperledger Fabric for the execute order validated paradigm. Note that we ignore permissionless blockchains as their performance is solely decided by the consensus. And the consensus trade-off in security and performance is well studied. We first apply the YCSB workload and the smallback for their peak performance. Then we tweak the YCSB workload as shown in this table to differentiate the effects of each taxonomy dimension. On the peak throughputs of update query, we observe that the blockchain database gap between there are still there, but not as large as that Blockbench reported. We attributed the key reason is that HStore selected by Blockbench is an in-memory distributed database with primary backup replication. HStore represents an extreme point of the design space that makes rather dissimilar and incomparable to blockchains. However, under the skilled smallback workload, the gap drastically shrinks. In particular, when switching from unified YCSB to more complex smallback, the performance of Fabric degrees and Quorum improves. In later experiments, we managed to account the former due to the workload skewness, while the latter due to the larger record size. Our major finding on replication is that the transaction replicated model restricts concurrency, limiting the impact of replication approaches and failure models. This conclusion can be demonstrated by comparing Fabric and TiDB. Fabric's update latency increases when systems are overloaded. It is because blocks pile up in a queue, waiting for their sequential validations. Even inside a block, transactions commit their effects sequentially based on their internal order. Worse still, substantial overhead in transaction processing is attributed to security factors rather than data processing. This security overhead can be more evident in the delay breakdown of the query, which does not involve the sequential consensus and validation. To investigate the failure model, we focus on quorum with rough to tolerate crash failure, and then switch to IBFT for Byzantine failure tolerance. Counterintuitively, we haven't observed substantial changes even though IBFT incur more messages on the bandwidth. We attribute it again to the sequentiality constraint in blockchains that limited the concurrent consensus instances. The difference between crash failure tolerance and Byzantine failure tolerance is more manifest in their behavior stability. This is quantified by the standard variation as the bar line illustrates. It is because Byzantine fault tolerance requires a response from a larger set of peers. Otherwise, it would undergo the expensive field change to replace the leader. During this time, the service is unavailable. In this experiment, we increase the number of nodes to differentiate the effects of replication approaches. Fabric is the only Sherlock system. Even though Fabric also employs the rough consensus to obtain the transaction order and form the ledger, this is an external service with 6 fixed orderers. The increasing number of Fabric peers consume the shell order log where all the other systems, all their nodes participate in the consensus. Contrary to our expectation on the two blockchains, we do not observe the expected constant performance of a Sherlock system in Fabric, nor performance degradation in a consensus-based system in Quorum. This is because the endorsement policy in Fabric requires a transaction to be endorsed by all the nodes. Hence, more nodes need to wrap transactions with more signatures and therefore longer validations. Due to the sequentiality in transaction-based replication, this increase in validation time translates to the throughput decrease. On the other hand, Quorum underutilizes Raft, making its performance less sensitive to the consensus group size. Specifically, Quorum pre-execute transactions at the tip of the ledger before batching these transactions into a block for the consensus. Thus, the block proposal is affected by the ledger's sequentiality. This sequentially explains why, under the same Raft protocol, the new SQL database EDCD achieves higher peak performance compared to Quorum, but its performance decreases with the number of the consensus nodes. The new SQL database TiDB does not exhibit a constant or a decreasing performance trend. In our extended paper, we attributed it to the interplaying effects between the transaction storage layer along with a growing number of nodes. On concurrency, executed order validated blockchains have low performance under workloads with high contention and constraints compared to order executed ones. Workloads impact the most on new SQL databases than in NoSQL ones. This can be seen from the following behavior. In blockchains, Fabric throughput degrades when transaction gets more skilled access or modify more records per transaction, while Quorum drops when updating larger record size. Similar pattern also holds between new SQL TiDB and NoSQL etcd. Here, we take a close look on the record size. We enlarge the record size in a uniform update workload to increase the complexity per transaction without exaggerating the inter-transaction conflicts. As shown on the left, all the databases exhibit moderate throughput decrease and latency increase. However, the two blockchains behave differently. When the record gets larger, Fabric performance remains roughly constant, but Quorum suffers a significant drop in throughput. From the latency breakdown on the right, the block commit time in Fabric only doubles, whereas in Quorum, there's a 70 times increase. It is because for each commit, Quorum's virtual machine needs to reconstruct a Merkle patriarchal data structure which involves many expensive cryptographic computations. At the same time, the cost of a hash function increases with the record size. Another reason is that Quorum adopts the order execute architecture. It executes transactions twice, first during the block proposal and the other during the block validation or commit. Hence, its performance suffers from the double execution. However, in Fabric, the serial processing only occurs once during the commit phase. Hence, when the transactions are computational heavy, execute order validated blockchain outperform order execute ones by introducing the sequentiality later. But compared with blockchains, NewSQL database with storage-based replication can harness more concurrency. On storage, we find the ledger abstraction in blockchains incurs significant storage overhead. The overhead needed to guarantee the verifiability is small. This is shown by decomposing the storage in Fabric and compared with TiDB. We additionally compare the space consumption of two self-verifiable data structures, Merkle patriarchal tree in Quorum or Ethereum and Merkle bucket tree in old version of Fabric. We observe the former demand for more space. The performance of sharded blockchain is far behind that of distributed database due to the security requirements on shard formation and periodic reconfiguration. This conclusion is made from comparing AHL, a state-of-the-art sharded blockchain, with TiDB and Spanner and Google Cloud, with scale to 48 nodes. Even though all systems exhibit horizontal scalability, the throughput of AHL is far behind than two databases. In the meantime, it further decreases 30% if we turn on the shard reconfigurations. Periodic shard reconfiguration is to mitigate adaptive adversaries. These adversaries can leverage membership information to corrupt certain shards. The following diagram proposes a simple and heuristic framework for the back-of-the-envelope performance forecast for blockchain database hybrids. Drawn from our experimental insights, we position the replication model, whether the storage replication or the transaction replication, as the foremost factor. And then it comes with the failure model. We expect the gap between the CFT and the BFT is much closer in transaction-based transaction replicated system than in storage replicated ones. The chart on the right draws out our predicted range and their reported write throughput. Using the two factors stated above, we can predict the write throughput effectively. For instance, the validators exhibit better throughput than Chainify because it uses storage-based replication and crush failure tolerant protocols. But its performance is expected to have a higher variance because on the high contention, the throughput can decrease significantly. In conclusion, our major contribution is a unified taxonomy for blockchains and distributed databases. We decouple the taxonomy into the following four independent dimensions, including replication, concurrency, storage, and sharding. The taxonomy provides a common framework to analyze existing and future hybrid systems for their security performance trade-off. In the meantime, we selected for the benchmark the following representative systems. etcd to represent NewSQL database, TiDB to represent for distributed databases. And we select Fabric as the representative for permission blockchains with execute order validated architecture, and Quorum for more conventional order execute architecture. Our experiments differentiate the implementation of each dimension and evaluate their peak performance so that we provide a back-of-the-envelope performance forecast for future hybrid systems. Thank you.